Hello, today we are starting nuclear chemistry. This is one of my favorite units of the year because it has some very interesting subtopics in it that will lead to a lot of great discussions in class, like nuclear power, nuclear medicine, nuclear warfare. What we are going to do in today's video is we are just going to start with some basic definitions and talk about how to balance nuclear reactions. So in this slide here, we're just going to start talking about what is a nuclear reaction. So a nuclear reaction is a reaction that involves changes in the nucleus of the atom. And that's why we previously reviewed protons, neutrons, electrons. Those are going to be very important for this unit. Nuclear reactions are going to look totally different than regular reactions. So down here we have a regular reaction. So this is what we call our chemical reactions. So in this we have CH4, which is methane, plus oxygen gas makes carbon dioxide and water. So we start the reaction with one carbon, we end with one carbon. We start with 4 oxygens, we end with 4 oxygens. In our normal chemical reactions, we have just a rearrangement of the atoms. So we have some bonds breaking, some bonds forming, rearranging the atoms to form new products, but you keep the same number of C's and H's and O's that you have at the beginning and that you have at the end. Nuclear reactions look different. In nuclear reactions, you will start with one atom and you will end up with a totally different atom. So we will have to balance these equations a little bit differently. All right, some vocabulary. A radioisotope is an isotope that is radioactive. So we already reviewed isotopes, same element, different mass, such as carbon-12 and carbon-14. Carbon-12 is stable and not radioactive. Carbon-14 is unstable and therefore radioactive. So in this unit, we are going to be talking a lot about some of our less common isotopes because those are the ones that are radioactive. Now, radioactive isotopes can be naturally occurring, such as carbon-14. It's naturally unstable and decays, or they can be produced artificially through a reaction where you fire high-speed particles at them, which then penetrate the nucleus and then cause the changes within the nucleus. All right, stability. Like I said, carbon-14 is unstable and therefore radioactive. So we need to talk about which things are and are not stable. So first off, if anything has an atomic number greater than 83, it is unstable and therefore radioactive. So on the periodic table, anything with an atomic number greater than 83 will be radioactive and unstable. And we are going to be using some of the elements down at the bottom of the table that we don't normally talk about much. We will be using them here because they are radioactive. All right, there's another thing that affects the stability. When you look at the ratio of protons to neutrons, the closer that ratio is to 1:1, the more stable you could predict that that particular isotope would be. For example, in carbon-12, 6 protons, 6 neutrons, so it's got a perfect 1:1 ratio. Carbon-14, 6 protons, 8 neutrons, so as you start to deviate from that 1:1 ratio, it's more likely to be unstable. And then lastly, take a look at reference table N. Reference table N is called selected radioisotopes. So if it shows up on table N, it has to be radioactive and unstable. So we will be using table N with this unit. First off, just to find some things that we know are radioactive and unstable. Also when we do our half-life calculations and when we write out some of our reactions. All right, nuclear reactions involve changes in the nucleus. So you start with one element and you actually end up with a totally new element. Those are also called transmutations. So nuclear reactions are transmutations because you change from one element into another one because there is a change in the nucleus and a change to the atomic number. So if you think about last year in bio, mutation was a change in the genetic material. So mutation is a change, but this is now the chemistry version. So it's a change from one element to another one. All nuclear reactions are transmutations, and they can happen either naturally. So if you have something that's naturally unstable, like carbon-14, it will undergo a natural transmutation, or artificially. So that would be where you take something and you hit it with a high-speed particle and then trigger the transmutation. That would be artificial. All right, in a natural transmutation, as we were saying on the last slide, this occurs naturally, spontaneously on its own. So you will always start with just one particle. So in this example here, we're starting with just potassium. If this was an artificial transmutation, we would see two particles, potassium plus something else. So we have potassium transmutating, changing into argon and then a positron. We'll talk more about what a positron is in the next video. This example down here, they give us the picture version of it, but basically we're starting with uranium with a mass of 238. The atomic number for uranium is 92. Single reactant undergoes a transmutation naturally, changing into helium and thorium. Thorium has a mass of 234 and an atomic number of 90. Now, balancing these reactions. The way that we balance our nuclear reactions, because we can't count the number of uraniums on both sides of the equation, because they're not on both sides of the equation, is you balance out the top numbers, your mass, so 238 equals 238. Bottom numbers, your atomic number, also has to be balanced. We look at this top reaction here, 37 on top, 19 on the bottom, 19 on the bottom. So just balance these differently. All right, here we have artificial transmutation. So in order to be a transmutation, it will change from one element into another. And in order to be an artificial transmutation, we will see two reactants, so two substances before the arrow, as opposed to natural transmutation where you only have one reactant. So in an artificial transmutation, the change is brought about by hitting the particle with another fast-moving, high-speed particle that hits the nucleus and then causes the nucleus to break apart. So we have our two reactants, so that would show us that it's an artificial transmutation. And again, we're still balanced. It's just a different way to balance. So top numbers, mass adds up to 33, adds up to 33. Bottom numbers, the atomic numbers, add up to 16 and add up to 16, so it is still balanced. So we've already started working with this. In our nuclear reactions, our mass is still conserved, but we're going to show that differently because we can't count the number of hydrogens on both sides of the equation because they will not be there. So the mass, top number, and the atomic number, which is the bottom number, the number of protons, must be the same on either side of the equation still. This slide here just serves as a reminder. The top number, the superscript, is the mass number, which is the protons plus the neutrons. And the bottom number, the subscript, is the atomic number, and that tells us the number of protons. Now, if we had this helium with a mass of 4, they don't have to include the 2 down here at the bottom, because we could look at our periodic table, find helium on there, and know that its atomic number is 2. So a lot of times they won't fill this in for you, and you can figure that out from the periodic table. For example, if we have uranium, with, let's say, a mass of 238. We look at the periodic table. Uranium is way down there in that bottom section, and its atomic number is 92. So we could go ahead and fill in the atomic number if they do not give it to us. All right, now we just have 3 examples to go through where we have a missing particle and we have to figure out what it is using the balancing that we've been talking about. So we cut it in half at the arrow. 6 and 1 adds up to 7. So therefore my missing particle must have a mass of 3 so that my atomic or my mass numbers add up to 7. Bottom numbers need to add up to 3. So this must have an atomic number of 1. Then we go to the periodic table in order to figure out its identity. So atomic number of 1 would be hydrogen. So my missing particle was hydrogen with a cut it in half at the arrow. Top number mass has to be 14. So my missing particle must have a mass of 14. Bottom number must be 6. Atomic number must be equal to 6. So blank minus 1 equals 6. So our missing atomic number would be 7 because 7 minus 1 equals 6. Then you go to the periodic table. You look at the atomic numbers, which is the bold number, and atomic number 7 is nitrogen. So our missing particle was nitrogen with a mass of 14. All right, last one, cut it in half at the arrow. Mass is 53. We got 0 there, so my missing mass must be 53. Notice they did not fill in a bottom number here, an atomic number. No big deal. Take a look at your periodic table. On your periodic table, find iron. Iron has an atomic number of 26, so we fill that in. And then X would have to be 25 because 25 plus 1 equals 26. So our missing element is Mn because that's atomic number 25 with a mass of 53. Now, one last thing I want to do is identify these 3 equations as either an artificial or a natural transmutation. So, easiest way to do that is see how many reactants we have. So in number 1, we have 2 reactants. Therefore, this would be an artificial transmutation. Okay, number 2, we only have 1 reactant. So therefore, we have a natural transmutation. And in number 3, that would also be a natural transmutation because we only have the 1 reactant, so the change was brought about naturally. It did not have to be initiated by something else. And these are all transmutations because they start as 1 element and turn into another element because the atomic number has been changed. All right, so now we want to do the worksheet on balancing nuclear reactions. It's basically like these 3 examples. You just figure out your missing particle.